Okay, welcome back everyone. In this video we're going to be looking at conservation of mechanical energy. And so again we're trying to look at the difference between conservative and non-conservative forces. We want to look at what the law of conservation of energy is, and then also start to examine the concept of a system and what it means to have a system and its environment. So basically a system in physics is anything that you say it is. Okay, so you take an object or a collection of objects and you draw a circle or a boundary around it, and that's your system. Because technically the largest system that we can have is the universe, but analyzing that is sometimes a bit more complex than we can handle. Everything not contained in the system is what we call the environment. And then we have a boundary that separates it. Now, conservation of energy tells us that inside of our system, if it's isolated, okay, and the boundary is like a fence that keeps everything in, then we could write that the total energy is equal to potential plus kinetic plus internal energy. Now this internal energy here has to do with the individual motion of the molecules. Okay, so this is kind of like a thermal energy, if you will. So we won't get too much into that, and for the most part we're going to assume that systems are made up of point particles that don't really have thermal energy, and we'll just be looking at U and K. So we're going to say that no mass can enter or leave, no energy can enter or leave, and therefore energy is constant or conserved for a system. So here's another view. Inside of the system, we're only going to allow potential and kinetic to interchange or to go back and forth. And so here's what we talked about in the last video, that energy is potential plus kinetic, and it's equal to a constant. So that means that the changes are equal to 0. So if delta E is equal to 0, this is where we're getting that delta U is equal to negative delta K. So just to review that. Now for gravity, we can have kinetic and potential. And if you look at this, we are assuming a couple things. First of all, that we're near the surface of the Earth, because that allows us to use 9.8 for G. Secondly, we're assuming that we don't have rotation, because that would change our kinetic energy equation. And so those are two assumptions for that. If we had a spring, then we are assuming that this is a spring that obeys Hooke's law, so F equals kx. If we had a nonlinear spring, so F was some weird function of x, then we would have to integrate to get the potential energy function. So for example, let's think about the energy in a pendulum. So the pendulum is going to swing back and forth, and it's going to rise to a maximum height of h. And if that's the case, then initial kinetic plus initial potential equals kinetic plus potential. And sorry about that, that should say this is for any 2 points in the pendulum's swing. Okay, now one thing to point out is that if this is a length of L and this is a height of h, an angle of theta, and we want to get a height of h, we can show that h is equal to L 1 minus cosine theta. And the way that we get to this is by noting that this is L cosine theta, and that this distance right here, this is L cosine theta, this is h, but the entire distance all the way down is L cosine theta plus h, which must be equal to the entire length. We solve this for h and we get L 1 minus cosine theta. Okay, now what about springs? Well, springs start at an equilibrium point of 0, and as they compress, they get a displacement, and as they extend, they get a displacement in the positive direction. And so therefore, potential at one point plus kinetic at one point is equal to potential at another plus kinetic at another. So it doesn't really matter which 2 points we pick. And we'll analyze the mass on a spring a lot more when we get to chapter 14. Okay, so here's an example. We have a single conservative force of F equals 3I plus 5J. And it's going to act on a particle that's 4 kilograms. We want to find the work if the particle, if it moves from the origin to r equals 2I minus 3J, and we want to see if this depends on the path. So first of all, the work is going to be F dot r. So that's going to be 3I plus 5J dotted with 2I minus 3J, and we have newtons and meters, so that's going to give us joules. So that's going to give us 6 minus 15 is going to be negative 9 joules. Okay? And so that's our work. And the question is, does this result depend on the path? Well, so let's draw a picture here and let's break things up. So the force is 3, 5, so it's a constant force this way. And we're ending up at the point 2, negative 3. Okay, so that's r. Now, it turns out that there's another way to get to that point. Okay, what if we go over 2, and we'll call that x, and then down, we'll call that y. So x is equal to 2I hat, and y, vector y is equal to 2j hat. And let's see if breaking r up into these 2 legs of the triangle, let's see if that gives us a different amount of work. Okay, so we'll have work along path x is going to be F dotted with x, so that's 3I hat plus 5j hat, dotted with simply 2I hat. That's going to give us 6 plus 6 joules. And then the work along path y will be F dot y, and I think you see what's going to happen here. Same force, but now we just dot with negative 3j hat. That's negative 15 joules. That's a total amount of work on a different path of negative 9 joules. So, no, the result doesn't depend on the path. Okay, so it's path independent. And as a matter of fact, when you have a force that is constant like this, that doesn't depend on where you are, then it's typically going to be path independent. Now, if we had a force that looked like this, maybe it was 3x I hat plus 5y j hat, so that the force was actually getting bigger as we were moving in the positive x direction. Well, this definitely would have an effect on our result. And that would not be path dependent, or path independent rather. Okay, so now we want to find the speed of the particle at r if its speed at the origin was 4. So this is the work-energy theorem. So the work is negative 9, and the change in kinetic energy will be 1/2 m v final squared minus v initial squared. So this means that v final is going to be about 3.4 meters per second. I left out a little bit of algebra, but we can just focus on the setup here. And this was 9, negative 9. Okay, and so what is the change in potential energy of the system? Well, we've said this a couple times now, but the change in potential energy is equal to the negative work that's being done. So it's negative 9, or just positive 9 joules. Okay, let's try another example. A bead slides on the loop-de-loop as shown. If it's released from height h equal to 3.5 r, what's the speed at point A, and how big is the normal force at A if the mass is 5 grams. Okay, so we can use conservation of energy and say that the energy at the top is equal to the energy at point A, and the energy at the top is just going to be potential, which is going to be mgh at the top, whatever that is. And at point A, we're going to have mgha, and that's going to be moving, so we'll have 1/2 mva squared. Okay, so the m's are going to drop out, which will happen if you have potential energy due to gravity, but not if it's from a spring. Okay, so 3.5 r times h is equal to g times 2r, because our height right here is going to be 2r, and then plus 1/2 va squared. Okay, and I dropped a g here. Okay. Oh, and I don't have an h because h is 3.5r. Okay, so I take that and I bring it over to the other side. Okay, and I get 1.5 gr is equal to 1/2 va squared. This means that va squared will be 3 gr. So va is root 3 gr. Okay, and I could plug in 9.8, etc. if I wanted to, but we could just leave it as an expression. So how great is the normal force at A if the mass is 5 grams? So let's draw the top, and here's point A, and at point A we have a normal force downwards and gravity downwards. So this is a review of chapter 5 and centripetal force. So net force Fn plus mg is equal to m v squared at point A over r, not over 2r, just over r. So this means that the normal force is going to be m v squared a over r minus mg. So it's going to be m. Now v squared is actually just 3gr. Divide that by r, and we've already factored out an m. So those r's nicely cancel. So the normal force will be equal to 2 mg. Okay, so you could plug in 2 and 0.005 kilograms, 9.8, and whatever that gives you, but it's going to be pretty small. Okay, so that about covers it for this lecture. Next time we're going to talk a little bit more about non-conservative forces, and also we'll talk about potential energy functions.